All right. Good afternoon. Excuse me. Good morning. Okay, I must be in another time zone. Okay. Happy Friday, anyway. Now, for what we have in continuing on with polynomial division, and we have on page 280. Okay, and just going back to what we have had with line division as well as synthetic division, and making the crossover to the remainder and factor theorems. We have on page 280, again, we have a polynomial with x to the fifth plus 32, and we have divided by x plus 2. And for what we have in the case of the long division setup, okay, all right, so you have x plus 2 taken into x to the fifth plus 32, and again, just in the long division setup, okay, I have both the divisor and the polynomial dividend arranged in descending degree order. So I have x plus 2. And again, for the dividend, I want all the degrees, okay, in x from the highest order down to the constant to be represented. And here we have missing degree terms from the fourth order down to the first order. So I'm using zeros for the placeholders. Now, for this item, okay, as I look at translating what I have in terms of synthetic division, okay, so I have taking the 0 of x plus 2. Okay, so we have x plus 2 is equal to 0, and we have that x is equal to negative 2. And I'm going to add in, okay, just another description since I'm going to be working with the remainder theorem. Okay, so we have, in the remainder theorem, you have this item that's in reference to f of c, and c is going to be the 0 of the divisor, so we can say that x is equal to c is equal to negative 2 as well. Now, for what we have going from the long division to the synthetic division setup, and following through with performing synthetic division. So we have negative 2 to be isolated. And on the other side of the vertical partition, okay, we have the coefficients of the dividend. So we have for x to the fifth, okay, again, you read this as 1x to the fifth, and then we have 4 zeros to follow. Once again, signifying that we have missing degree terms in x. And again, we want the polynomial to close out with a constant. And again, we have that number to be 32. And initiating the long division, we have, once again, the leading coefficient of the dividend is also going to be the leading coefficient of the quotient. And as we bring down 1, we have 1 multiplied by negative 2, and the product is negative 2, so this will be taken to the next column. And again, with synthetic division, we are performing column by column addition. So we have 0 plus negative 2 is minus 2, and then we have negative 2 times negative 2 is positive 4. Then we have 0 plus 4 is 4. Then we have negative 2 times 4 is negative 8. Subsequently, we have 0 plus negative 8 is minus 8. And then we have negative 2 times negative 8 is 16. And we have 0 plus 16 is 16. And then we have negative 2 times 16 is negative 32. And we have, with the last column total, we have 32 plus negative 32 is 0. And so we're going to have that the remainder is equal to 0. And looking at what we have in the determination of the remainder through not only the synthetic division but also through the remainder theorem. And for what we have in the case of the remainder theorem. You're looking at, once again, the polynomial f of x, or it could be g of x, h of x, z of x, divided by a linear expression in x. Again, to be able to use synthetic division, the divisor must be first order in x. If I have something like x squared or x cubed, or something like x to the 1/2, but it's not x to the first, you cannot perform synthetic division. Now, in the case of the remainder theorem, you don't have those constraints quite so much. And for the remainder theorem, again, we have, in brief, if you have a polynomial f of x is divided by x minus c, then the remainder is f of c and through using the remainder theorem. Okay, so we have for f of x, again, this is equal to x to the 5th plus 32 as for the remainder. Again, we have the remainder is equal to f of c, and with regard to that function, f of c again is going to be f of -2 and inputting -2. So again, your input, you have x equal to c is equal to -2. And so we're going to have -2 raised to the 5th, followed by the addition of 32. And -2 to the 5th, okay, we have it -32 plus 32. And that is equal to 0. And notice we have, for the results, regardless of whether you use synthetic division or long division, or in this most recent case, the remainder theorem, okay, we're going to have the exact same result in the remainder. All right, and also looking at what we have concerning the use of the remainder theorem, and we have for 36, now we're going to have a bit of history to repeat in the dividend that we have in this problem, like what we have for number 35 with x to the 5th plus 32. You're going to have some missing degree terms in x. And for what we have in 36, now we have x to the 4th minus 81 divided by x plus 3. Once again, for the long division setup, once again, the reason I'm doing this is to make sure I'm not missing any necessary 0 placeholders in case there are missing degree terms in x. So we have x plus 3. Again, we have taking into x to the 4th, and again, you have a spread, a void, between x to the 4th and negative 81. So we have a missing x to the 3rd and a missing square term, as well as a missing x term. And we have followed by negative 81 and translating what we have in terms of synthetic division. Okay, so we have x plus 3 is equal to 0, and we have that x is equal to negative 3 and again we have x is equal to c is equal to negative 3. And so for what we have in the case of synthetic division, alright, so we have negative 3 isolated, and once again we have to the right we have lining up the coefficients of the dividend. So we have 1 followed by 0 and another 0 and another 0, and then we have last the constant negative 81. And in looking at what we have with the synthetic division, so bringing down the coefficient 1, we now have the first product to bring over into the next column. Okay, we have negative 3, and we have 0 plus negative 3 is minus 3. Negative 3 times negative 3 is 9. 0 plus 9 is 9. Negative 3 times 9 is negative 27. 0 plus negative 27 is negative 27. And we have negative 3 times negative 27 is 81. And negative 81 plus 81, again, is going to be at 0. And once again, we have that the remainder is 0 once again. And for what we have concerning the remainder theorem, so once again we have with f of x, this is x to the fourth minus 81. And if you have a linear divisor, okay, think about the remainder theorem, you're looking at the function value, and also you're not having to worry about 0 placeholders. And again, so we have that the remainder is equal to f of c. And again, so this is going to be f of negative 3. Once again, the c was predetermined. And we have plugging in negative 3 for x in the polynomial. So we're going to have negative 3 raised to the fourth minus 81, and negative 3 raised to the fourth power is 81, and taking away 81, and once again we had the result to be 0. So once again we have the same outcome for the evaluation of the remainder. Alright, now for what we have in the case of the next item. So again, and I was asked this yesterday, okay, for those items where you can do synthetic division and the remainder theorem, will the remainder always be the same? And the answer to that question is yes. And if there's a difference between the values, that means that there was some wrong operative that was performed. Now, for what we have in the case 41, we have a function f of x, and we have is equal to 2x to the fourth minus 5x cubed, and we have plus x squared and we have minus 7. Okay, now we'll just go ahead and set things up in terms of synthetic division. Okay. And I'm just going to mention, okay, so just kind of rewrite what we have here. Okay, if you notice, we have f of x, you have 2x to the 4th minus 5x cubed plus x squared. And notice we have missing a first order x term. So we just write this as 0x minus 7. And for what we have in the case of part A, and let me stress this. So you have f of x equal to 2x to the 4th minus 5x cubed plus x squared minus 7. And this is going to be divided by x minus 4. And again, just for the setup. So the divisor is x minus 4. And if I set this equal to 0, so we have the 0 is going to be x is equal to 4. And on the side of utilizing the remainder theorem, okay, so you have the x is equal to c is equal to 4. And we have regarding, okay, the remainder theorem. And we have for part A, you have that the remainder is equal to f of 4, and plugging in 4 for c or x, we have 2 times 4 to the 4th minus 5 times the cube of 4, and we have plus 4 squared minus 7. 4 to the 4th. Okay, so this is going to be at 256. We have minus 5. Now 4 cubed is 64. 4 squared is 16. And we have minus 7. And in the follow through, so we have 512. Minus 320, and we can go ahead and write the difference, 16 minus 7, so that is going to be at 9. And for what we're going to have for the remainder, okay, through the use of the remainder theorem, okay, this will come out to 201. And for what we have in the case of part B, okay, and it says here to determine the remainder of f of x divided by x minus 4. Okay, so we have, again, with the remainder theorem, at f of 4, and in carrying out what we have through the use of synthetic division, again, so we have the 0 at the value of 4. And taking the coefficients of what we have with the dividend. Okay, so just fully rewriting this polynomial where all the terms in the degree x as well as the constant are going to be on display. So just placing the coefficients in the synthetic division setup. So we have 2, negative 5, then we have 1, then 0, and finally negative 7. Okay, so we have with the remainder theorem, which we had the outcome to be 201, and comparing to what is going to be the output, namely the remainder, okay, from the synthetic division. Okay, and so with synthetic division, the leading coefficient from the dividend is going to be brought down. So we have 4 times 2, so we have 8. Negative 5 plus 8 is 3. And then we have 4 times 3 is 12. 1 plus 12 is 13. 4 times 13 is 52. 0 plus 52 is 52. 4 times 52 is 208. And negative 7 plus 208 comes out to 201. Again, so you have the remainder is at 201. And that's going to be the same as the remainder through the use of the remainder theorem. Okay, so you have this bit of history to repeat. Now, for what we have in the case of number 42, okay, so you have a polynomial, and this time we're going from f of x to g of x. And g of x, we have set equal, okay, to negative 3x to the 5th. And we have plus 2x to the 4th. Plus 6x squared minus x plus 4. And this polynomial, okay, is divided by x minus 2. So we have with the divisor, okay, so we have just going ahead and getting to the 0. So if x minus 2 is equal to 0, we have that x is equal to 2. And we have that x is equal to c is equal to 2. And for part A, okay, through the use of the remainder theorem, again, so we have with the remainder, okay, so this is going to be g of c, which we're going to have as g of 2 so we have negative 3 times 2 to the 5th, and we have plus 2 times, okay, 2 to the 4th, and we have plus 6 times the square root of 2, and we have minus 2, and we have plus 4, and 2 to the 5th is going to be 32, and 2 to the 4th is 16, and we're going to have plus 6 times 4, and negative 2 plus 4, we can go ahead and cluster these together as plus 2. And to end the follow through, okay, so you have negative 96 plus 32 plus 24 plus 2 once again. And we're going to have the negative 96 to have its minus side to outweigh the plus side of these positive terms all put together. And so we got negative 96 plus 32 is negative 64. Negative 64 plus 24 is negative 40. And negative 40 plus 2 comes out to minus 38. Now, looking at what we have on the side of synthetic division. Okay, so we have here, again, so we have g of x. I'm just going to rewrite this with indicator of a missing item. We have in the fully expanded polynomial form of this dividend, so we have negative 3x to the fifth plus 2x to the fourth. Notice we are missing a cubic term. So 0x cubed plus 6x squared minus x plus 4. And again, just setting things up in the realm of synthetic division. Okay, so again, we have the 0 of x minus 2 is going to be at 2. And setting things up, so we have for g of x, again, we have the coefficients negative 3 and 2 and 0 with regard to the missing cubic term in x. Then we have 6, then negative 1, and then 4. So we have with synthetic division. Okay, so we bring down the leading coefficient, negative 3. 2 times negative 3 is negative 6. 2 plus negative 6 is negative 4. 2 times negative 4 is negative 8. And then we have 0 plus negative 8 is negative 8. 2 times negative 8 is negative 16. And we have 6 plus negative 16 is negative 10. 2 times negative 10 is negative 20. 1 plus negative 20 is negative 21. And 2 times negative 21 is negative 42. And 4 plus negative 42 is negative 38. And again, so we're going to have here, okay, the remainder is negative 38 from the synthetic division, and this will be identical to what we have in the case of the remainder theorem. So we have that history regarding the remainder to repeat. All right. Now, for the next item, okay, we're going to have the factor theorem to be included, and just taking what we have regarding the remainder theorem. Okay, so we have with the remainder theorem, if f of x is divided by x minus c, then the remainder is f of c. And for what we have regarding the factor theorem, okay, so if we have if the remainder f of c is equal to 0, then you're going to have x minus c is a factor of f of x. On the other hand, if the remainder f of c does not equal to 0, then it's going to turn out that x minus c is not a factor of f of x. And we have tying in, okay, these theorems, and we have for the case number 48, okay, and for the second part, I'm going to apply a little bit of brevity because some of the operations can get a little bit long-winded. And for number 48, okay, now we have a polynomial function, once again, with g of x. And this is set equal to 2x to the fourth plus 13x cubed minus 10x squared minus 19x plus 14. And for what we have for the first question, and this is going to be, is c equals -2 a 0? And another way of asking this would be, is x plus 2 a factor of g of x? And we have with the remainder theorem and subsequently the factor theorem, okay, we'll determine whether the answer is yes or no. So we have this given polynomial, and we have with the remainder, as we take x plus 2 into this fourth degree expression. Okay, so we have g of -2 is equal to 2 times -2 to the fourth Then we have plus 13 times -2 raised to the third minus 10 times, okay, the square of -2 minus 19 times -2 plus 14. And we have, and following through, okay, so we have 2. Now -2 to the fourth is going to be 16. -2 to the third is -8. And we have -2 squared is 4. -19 times -2 is 38. And we have plus 14. And 2 times 16 is 32. And then we have minus 104. Minus 40. And 38 and 14 put together, okay, we have it 52. And it's going to follow that we have the remainder is going to be -60. Okay. And now in the context of the remainder theorem, okay, so your remainder, theoretically, instead of f of c, this is going to be g of c, but we still have the same rules to apply. And since the remainder g of c is equal to g of -2 is equal to -60. So we had this to be the remainder, and this does not equal to 0. It is going to be by the factor theorem. that negative 2 is not a 0, and to add in, okay, so x plus 2 is not a factor. Of g of x. Now for the second part, okay, so negative 2 is not a 0, so x plus 2 is not a factor of g of x. Now we have for part B, okay, we have determining whether c equals negative 7. Again, we're determining whether c equals negative 7 is going to be a 0. And that's just another way of asking, is x plus 7 a factor of g of x? So we still had the same polynomial function, but now the input, instead of negative 2, we now have it negative 7. So we're kind of running through the process. So we have 2 times negative 7 to the 4th plus 13 times negative 7 to the 3rd. We have minus 10 times, okay, the square of negative 7. Again, we have minus 19 times negative 7 plus 14. Now for negative 7 to the 4th, okay, we're going to have a large number with 2401, and negative 7 cubed, okay, we had to be highly negative at minus 343. And we have minus 10. Now the square of negative 7, okay, so we have at 49. Now negative 19 times negative 7 is going to be 133. And we have plus 14. And what's going to happen is that as we take the products, add together along with 147 after clustering together, 133 and 14. Okay, ultimately this sum is going to come out to 0. And for what we have now, okay, since the remainder in this case with the input at negative 7 is equal to 0. Again, just to repeat, so the remainder is equal to 0, so that is equal to 0. And so the answer to this question is now going to be that negative 7 is a 0. And also you have x plus 7 is a factor of g of x. So where negative 2 did not quite pass muster, negative 7 does. Now, again, we've had polynomial division and modes of finding out the quotient and remainder. And we're going to be sort of clustering together like stuff going back to the early days of looking at the FOIL method and factoring, and tying in what we have had with the remainder theorem as well as the synthetic division. And for this particular part, we have all these elements or concepts intertwined. We have for the next part, and this is going to be determining I'll give this a little different title here. Say you have determining factorization of polynomials from given zeros. Okay. Now we work with given zeros, like in the formation of polynomials in both factored and expanded form. But now for the factorization of polynomials, okay, we'll have a zero that is given, and I'm going to use that zero, not in the case of right away displaying a factor in x. So what I'm going to do here is take the zero and have that as the zero that is isolated in the synthetic division. Okay, and let's say that if you have, for instance, okay, say if you're looking at factoring and we'll say that we have here f of x, okay, is equal to 2x squared minus 6x plus 4 given that 1 is a 0. All right, so we have, looking at factoring, okay, so you have 1 is a 0, and again, I'm not taking right away like the expressing of f of x in factored form or expanded form, like say like 1 is a 0 of x minus 1, though we will get to this. Now in the realm of synthetic division, okay, so we have so you have 1 is the given 0, and we're going to take the coefficients of the dividend. So we have a square term, first order term, and a constant. Nothing is missing in degree x as we go from second order down to the constant. So we have 2, negative 6, and 4. So we have, with, once again, the use of synthetic division. Okay, so the leading coefficient from the dividend is going to be brought down. And then we have 1 times 2 is 2. And negative 6 plus 2 is negative 4. And then we have 1 times negative 4 is negative 4. And 4 plus negative 4 is 0. And let me mention, if 1 or whatever value is given as a 0 of the polynomial, and I run through synthetic division, I want the remainder after the synthetic division to be 0. And if it is not, it would turn out, say if I had like any value other than 0 for the remainder, this would signify that 1 is not exactly a 0 of this particular polynomial. But with the remainder at 0, 1 is officially a 0. And now for the items here, okay, so we have the remainder is equal to 0. Now for 1, kind of like when we were looking at forming factored and expanded entities in the polynomial. Okay, so 1 from the given 0, okay, and with 1 as a 0, we're going to have for the divisor, okay, that is going to be at x minus 1. Like if x minus 1 is 0, x is equal to 1. And for the 2 and the negative 4, we're going to have the quotient It's going to be a binomial expression since I have only two numbers in front of the remainder. So the 2 earlier was in reference to 2x squared, but with 2 brought down, and we have 2 underneath the bar, or after the round of synthetic division. Okay, that's going to be referencing not 2x squared, but 2x, and then we have minus 4. And so in the case of factoring, we're going to have the f of x is equal to 2x squared minus 6x plus 4. And that's going to be equal to the product of the quotients and the divisor. And in the case of Alex, he likes to stress the complete factorization. Okay, so you got the quotient, you have 2x minus 4. Notice we have even valued coefficients. So from this, I'm going to factor out 2. And 2 will go into 2x minus 4, x minus 2 times. And again, we have times the quantity of x minus 1. So for the complete factorization of 2x squared minus 6x plus 4, again, this is going to be 2 times the quantity of x minus 2 times that of x minus 1. And let's say that as another case. If I have, let's say, if we factor a third order expression, and we say that we have f of x is equal to 4x cubed minus 20x squared, and we have plus 33x minus 18. Okay, and we'll say that we have given that 2 is a 0. Okay, so we have here. Okay, so you have 2 as a given 0, and if we set things up in terms of synthetic division, so I want to double check my dividend, make sure that there is no 0 that needs to be placed. So you got x cubed, x squared, x, and a constant. So I can go ahead and put down 4, negative 20, 33. And negative 18 without having to put down 0 in between these numbers or even at the end. Okay, so with the synthetic division, okay, so 4 is brought down, and 2 times 4 is 8. Negative 20 plus 8 is negative 12. 2 times negative 12 is negative 24. 33 plus negative 24 is 9. Then we have 2 times 9 is going to be at 18. And negative 18 plus 18 is 0. And again, we want that remainder to be 0. Otherwise, 2 would not be a 0. This particular polynomial. Okay. So again, we had the remainder is equal to 0. Now, in the setup, okay, now just obtaining our variable expressions in the divisor and the quotient. So with 2, this will reference that the divisor is going to be at x minus 2. Again, like if x minus 2 is 0, x is equal to 2. And for what we have in the case of the quotient, so with 4 brought down, it's going to reference this time not 4x cubed, but 4x squared. And then we have minus 12x plus 9 So we're going to have f of x is equal to 4x cubed minus 20x squared plus 33x minus 18. And again, we have with the quotients, we have 4x squared minus 12x plus 9. And we have the divisor, so we have x minus 2. Okay, and this can be factored out further. So again, if you were to FOIL out 4x squared minus 12x plus 9 times the quantity of x minus 2, and if you used the geometric FOIL or box approach, you can have like a 3x2 or a 2x3 array, and combining all the terms, you would end up with this polynomial. Okay. Now, with 4x squared minus 12x plus 9, now the quotient can be factored because you have, like, if you think along the lines of factoring by grouping, you have like 4 times 9 is 36. And there are factors of 36 that will add up to negative 12, where we have negative 6 and negative 6. And if you were to factor, what would happen here is that this trinomial would have the same binomial factors with 2x minus 3 and itself. Again, we have times the quantity of x minus 2. And since 2x minus 3 repeats, so we're going to have the square of 2x minus 3 times the quantity of x minus 2. And the reason I'm stressing this part here is that there might be a run-in with an Alex problem where you might have the quotient and the remainder, and it turns out that the quotient is factorable and that the factor might repeat, and so you have to compress in this particular exponential mode. Right. And tell you what, just for the next few moments, and the factorization for this one will be complete with just the quotient and the divisor. I tell you what, let's see what we get in the case of factoring. And see, we have factor f of x is equal to 3x cubed minus 41x minus 28. And say we have given that 4 is a 0. Alright, for this item, okay, we can set things up along the lines of synthetic division. Okay, so we have that 4 is a 0. And for the dividend, okay, so again, just again, watch closely. Again, the coefficients, okay, so again, representing all the degrees in x. Okay, so you have with f of x. So again, we would have 3x cubed. Notice we do not have 0. We do not have an x squared in place, so we have using 0 for placeholder purposes. So we have plus 0x squared. And we have minus 41x minus 28. Okay. So just taking the coefficients, now we have 3 for x cubed, 0 for the missing x squared. We have minus 41 for the x, and we have negative 28. So in looking at what we have with the synthetic division, okay, so again, we have the leading coefficient from the dividend is going to be the leading coefficient of the quotient. So this is brought down. And then we have 3 multiplied by 4, so this is going to be at 12. And we have 0 plus 12 is 12. 4 times 12 is going to be 48. And then we have negative 41 plus 48 is going to be 7. And then we have 4 times 7 is 28. And negative 28 and 28 will form 0. So again, we have the remainder equal to 0. And on the basis that the synthetic division is done correctly, okay, this does affirm that 4 is 0. A 0. Okay, so we have for the divisor, okay, we have at x minus 4. And for the quotient, okay, so we have 3x squared plus 12x plus 7. So looking at what we have in factoring f of x. Okay, so you have 3x cubed minus 41x minus 28. And this is going to be equal to, again, we have 3x squared plus 12x plus 7. And we have times the quantity of x minus 4. Okay. And in terms of factoring in accordance with integer coefficients, this will be as far as we can go because we got 3x squared plus 12x plus 7. And if you were to think along the lines of factoring by grouping, well, we would have here the product of the first and the last coefficients with 3 times 7 comes out to 21. And there are no integer factors of 21 that will add up to 12. You can think of like 1 and 21, sum is at 22. And the other combination that is positive we have with 3 and 7. Again, that will add up to only 10. So this is going to be the complete factorization in the integer coefficients for this polynomial. So this does simply come out to the trinomial 3x squared plus 12x plus 7 times the binomial x minus 4. And now, in a partial continuation of polynomial division, and stressing not so much synthetic division or the FOIL method, but more in line with going back to the functions that are in the form of rational expressions and stressing the domain. And we have for this particular part, and this is over in the next section, I believe that is going to be section 2.5, and we have concerning domain and asymptotes of rational functions. Make that domain and vertical asymptotes of rational functions. There are other types of asymptotes we'll be looking into, but just for right now, we'll be looking at vertical asymptotes. All right. Now, see we have for a rational function, and we could say f of x, but I'm just going to designate a different variable. See we have for a rational function, r of x. we have by definition, okay, regarding domain. It's going to be a lot of repetition on this one, okay? So the domain, just like mentioned earlier, this is going to be the set of all values of x, or whatever the input variable is going to be. So we have the set of all values of x. Such that R of x is defined in the real number system. Now, so the domain, okay, so you had that bit of history to repeat. Now for vertical asymptotes, okay, now vertical asymptotes, now those are going to be vertical boundaries that will split R of x into different sections, or into separate sections. And are formed by exclusions from the domain as in the restricted values. Whose factors remain or will remain. And I'll stress this particular part, and this is going to be after R of x is reduced to lowest terms. And I'll give you just a couple of cases here where we have determining the domain and the vertical asymptotes. I'll give you one rational function that will already be in simplest form and another one that is not quite in simplified form. And we'll say we have, first of all, okay, so we'll have that r of x is going to be equal to x plus 1 all over x plus 4. Okay, so this rational function is already in simplest form, so there's no cancellation between the numerator and denominator involved. Okay, now for what we have in the case of the domain, okay, remember, for a fraction to be defined, okay, the bottom value cannot be equal to 0. So we have restrictions involve okay, the denominator. Okay, so you have x plus 4 cannot be 0. Okay, now you can have a 0 top part of the fraction as long as you do not have a 0 on the bottom. Okay, but definitely, okay, the bottom part of the fraction cannot be 0, so we have the x plus 4 cannot be 0. So you're going to have the x cannot be negative 4. And so only negative 4 is going to be excluded from the domain. So the domain is going to be the set of all real numbers with the exclusion of negative 4, and then displaying what we have in interval notation. So we have those values of x, okay, which will be less than negative 4. And we have along with those values of x, okay, which will be greater than negative 4. Now, concerning the vertical asymptote or asymptotes, okay, now r of x is already in reduced form. So that means that the denominator factor x plus 4 remains. And so for what this is going to signify, okay, is that the exclusion from the domain, which was negative 4, because its corresponding factor remains. That is, since it does not cancel out, this is going to signify that what was excluded from the domain, because the factor remains, you're going to have the vertical asymptote is going to end up being x is equal to negative 4. Okay, so the domain is exclusive of negative 4, but that exclusion, because we have the denominator expression to remain, since r of x is already in simplest terms, okay, that exclusion is going to be our vertical asymptote. And to provide a bit of a visual, okay, so just doing a bit of a quick sketch case. So we have the focus, okay, we have at negative 4. And x equals negative 4, okay, so that's going to be the vertical asymptote. Okay, now regarding the graph of the function for r of x, once again, this is just going to be a rough sketch. So you have one section of r of x, okay, you have like in this upper left-hand section, and x equals negative 4 splits up the graph So R of x is split up into these two distinct regions. And let me mention something as well regarding the vertical asymptote. Notice you have these two regions. Okay, you have the extremes, I should say in the middle. Okay, you have okay, this is going to run tangent to the vertical asymptote as y increases continuously, and as it decreases continuously at the bottom, this portion is going to run tangent, but it's never going to touch. So I'm just going to mention R of x never comes into contact it doesn't cross, it doesn't touch. So R of x never comes into contact with any vertical asymptote. Okay. Now for our next case, all right. So this R of x was already in simplest terms. Let's say that if we have a case where R of x is not as such. Okay, we'll say we have R of x is equal to x squared minus 1. And we'll say we have all over x squared plus 3x plus 2. Okay, so now this rational function is reducible. And now if we're looking for the domain, okay, you're going to be looking at what is not allowed to be equal to 0. In this case, you had the denominator. And you're looking for the domain before you do any kind of simplifying or reduction. So we have on the bottom, okay, so you have x squared plus 3x plus 2. So before any kind of simplifying is done, you're going to attain the exclusions from the domain. Okay, in this case, we have x squared plus 3x plus 2 cannot be equal to 0. And if that is the case, we have the factors cannot be equal to 0 either. So we have the factors at x plus 2 and x plus 1. So you have x plus 2 cannot be 0. Then we have x plus 1 cannot be 0. So we have two exclusions from the domain. So x cannot be negative 2 or negative 1. So we have with the domain, so you're leaving out negative 2 and negative 1. And with negative 2 as the smaller exclusion, okay, we have the domain starting out at proceeding from negative infinity. So we have those values of x which will be less than negative 2. And we have bypassing negative 2. And you will have those values of x between but not including negative 2 and negative 1. And with negative 1 as the second and last excluded value, the rest of the domain will be those values of x which will be greater than negative 1. So in interval notation, okay, we have these three subinterval sections that once again define what x can be for this rational expression. Now, where we have the asymptotes that run vertically to be concerned, okay, so again we have r of x is equal to x squared minus 1 all over x squared plus 3x plus 2. And if I look at factoring, so with x squared minus 1, we have from this difference to squares, okay, we have the quantity of x plus 1 times that of x minus 1. As for x squared plus 3x plus 2, so I'm going to have the quantity of x plus 2 times that of x plus 1. Notice we have a common factor with x plus 1. I'm just going to draw this out. Once more. Okay. So x plus 1, that's going to cancel out. And we're going to have for the completely reduced form of this rational function, this will come down to x minus 1 all over x plus 2. Okay. So for what we have here, okay, notice, okay, we have x plus 1 cancels out. Okay, so if x plus 1 cancels out, instead of becoming a vertical asymptote, okay, if you have cancellation of the factor and the cancellation of the factor is complete, in other words, if that factor vanishes from the denominator altogether, instead of being a vertical asymptote, this is going to be a hole in the graph. Okay, so if you got complete cancellation, that 0 is going to be not a vertical asymptote, but a hole in the graph. And as for what we have in the completely simplified form of r of x, okay, it turns out that x plus 2 remains. And since x plus 2 remains, okay, it's going to follow that in consequence, okay, the vertical asymptote is going to be x is equal to negative 2. Okay, now had there been no cancellations, I would have had two vertical asymptotes with x equals negative 2 and x is equal to negative 1. And just looking at how r of x will be displayed. Okay, so just, again, just applying a bit of a rough sketch here. Okay, so we have with the restricted values, again, we had at negative 1 as well as negative 2. Again, we have x equals negative 2. Again, this would be the vertical asymptote and the only vertical asymptote. And for what we have in the case of the graph of r of x, okay, so you have with r of x, okay, now in terms of how this is going to be carried out, okay, so you're going to have kind of like the function before. You have a bit of an arc, okay, in this upper left-hand region, and kind of like you have another arc in the sort of the lower right hand region. Okay, so you have starting out, and again, neither section touches the vertical asymptote. And as we get to where we have right at x approaching -1, so again, we have with these sections of r of x. Okay, again, so we have a vertical asymptote at x equals -2. Now for x equals -1, okay, we're going to have a hole in the graph. Okay, now this particular arc is going to run continuously, but for that one, you're not going to have to run continuously starting from the right of the vertical asymptote, because once you start from the bottom into the left, once you get to -1, okay, there's going to be a section of discontinuity. And again, so you're going to have a hole located at x is equal to -1. So for the exclusions in the domain, if you simplify the rational function, okay, there are two destinies, separate destinies, that will await the exclusions. If the factors remain in the denominator, then the exclusion will become a vertical asymptote. However, if the factor does not remain, as in canceling out completely, it's going to become a hole in the graph instead.